Thanks everyone for coming for the Hungarian Innovators monthly event. And we are a non-political organization of people involved in all kinds of innovation here in the San Francisco Bay Area. I would like to welcome Zsolt, our wonderful presenter who will be talking about all the wonders of the radar technology. And those who are online, please put your questions into the chat and I will be passing it on to the presenter. Thank you.
Thank you very much. So, my name is Zsolt, as Zoltán mentioned. I will be talking today about a little bit about radar, a little about the history, a little bit about the operation, a little bit what lies ahead of us, so what's the future and how we can operate with that. So, just a little bit about myself. I'm a Fulbright scholar, currently doing research at Kennesaw State University, and also an associate professor at the Budapest University of Technology and Economics. One of my research areas is radar technology. That's where we do also consultation in Budapest. We have different companies who mostly automotive, who are doing radar development, and that's going to be part of it as well. So the outline of my talk a little bit. First of all, I'm going to start with the history of radar with some good stories. It's always interesting to see what are the interesting stories behind this innovation. And then I'm going to talk about a little bit introduction to radar, how it's operating. I won't go too deep in the equations. I will have some minimal equations just to have some background on what we are looking at. And on the third point, as last, a little bit of details on the future of radar. So as we continue, so let's start with the history of electromagnetic waves, because that's the most important component in radar technology. Actually, what's important is that Maxwell and Hertz, they were in the 1800s. Maxwell was a pure mathematician. He started with electromagnetic waves, and he was the one who found the equations for the Maxwell equations, as we all know. And Hertz, he was a German guy. He was the one who actually were able to conduct measurements to prove that what Maxwell assumed from the mathematics was actually doable. And then the first presenter, the first application was Marconi. He was an Italian. He went to England and he started the first radio communication. That means he put up a first radio station and he was able to transmit voice messages with radio waves. And what's important is that there were already some people who assumed that some things were not actually working in the radio as they should be. So two things. One, when the commercial radio station started, already some complaints were there about interference, but they had no idea what's happening. So the listeners were calling about the interference, and there were some scratchy noise in the reception. Also, there were reported reflections of radio waves, which means if the weather was cloudy, some people were able to measure also these things and be able to hear the radio. And one more interesting thing is that in the story of Titanic, I think everybody is familiar with the story with Leonardo DiCaprio, the whole movie. The problem was that technically the Titanic was in 1994. There was no radar, no LiDAR, no any equipped equipment. The first one is in 1995, I think, was the Normandy, who used actually radio frequency to check if there were any ships available. That was the first application. It was not yet a radar. It was only trying to get some radio reception based on transmitting waves, and the other ships reflected, but they weren't able to really understand how these things happen. So that's the background of electromagnetic waves, and that's when it started. The British are the ones who invented radar. That's the basic story. And just a little bit on, it's a very funny story how they started. So before the Second World War, they already knew that the Germans were probably coming with bombers. So the big airplanes. And the question was in 1935 that the British government had a question. That's the biggest question on the slide. That's what I said. So can you do, us and the physicists were asked that, can you do a death ray? Somehow send out the electromagnetic wave and kill the pilots. Can you do that? And so Robert Watson-Watt was the first guy who actually calculated that you need about 5 gigawatts of energy to kill the pilots. And that's probably not going to work. You need actually to just have a glimpse, 5 gigawatts of power, that's about 2 atom reactors. That's about the power you need to build this ray. But the thing was that so Robert Watson-Watt said, okay, we cannot do that. So we have to find another way how to stop the bombers. And he had an idea that what they were able to do is send out the radio wave and get a reflection. And that reflection was able to be measured. And the thing is that when he had the hearing, because this was, as in all English government, you had a committee who were set up. And the story actually continues that his colleague, Arnold Wilkins, did a fast calculation when he was actually, Sir Robert Watson-Watt was presenting the idea that this is not possible, but the reflections are a solution. Sir Arnold Wilkins would also made a simple calculations. If you take 1 ampere of power, you use 30 megahertz of frequency, you can actually detect something from 6 kilometers. But this was only on paper, so they had no idea if it's possible or not. And this is actually the original letter when they say it's probably possible. And what was really good is all Englishmen, they were modest. That means that he stated that we did the calculations, but we're probably off with about a percentage of 10%. So, but it should be working. And this was in 1935. And the funny thing is that the government believed the physicists, and they said, okay, I'll give you the money. And they didn't have to do any extra work, no projects, no project proposal, nothing like that. He got the money, and he actually did his first experiment in 1935. So in the same year, he was able to do that. He used a simple Hayford bomber. That's actually a very nice picture of that. It's called the Daventry experiment, which means he went out. You can see it's in the countryside. He set up an antenna for the transmitter. He set up an antenna for receiver, and he was able to detect the reflections of this bomber. And actually, if you go to Daventry, you also have this very nice shield over there. That's the birth of radar technology. It was also from Robert Watson-Watt.
Question from the audience. What kind of oscillators did these guys use to create the waves?
They use clystrons. Yeah. We'll get to that. Yeah, that's a good question.
Another question.
Yes.
Is this what has anything to do with the?
No, that's not at all.
Not
No, that's worrying, but that's not the steam. Yeah, that's not a what. So after this first experiment, they built the whole chain home, the British. It's very interesting. This was the first radar system technically. What they did is they had these kind of large antennas, which they set up 20. So technically, you can see on the borders of England over here, you have 20 stations like this. And they built it in 4 years. So they were actually pretty right at the time, because of the Second World War, you will see the Battle of Britain, it was in 1942. So they were just in time to build this system. And what's important is they put up a system of 20 receiver and transmitter antennas, and it was able to detect the bombers from 100 miles, which gave them about 30 minutes of warning. 30 minutes is actually, in case of war, that's a lot of time, because they were able to do 2 things. They were able to react for the citizens, and the second thing, they were able to send up the counterattack. So this was the first system, and it was set up in 1939, or 20 such stations. It used a pretty large amount of power, but this was able to watch the skies for the German bombers. And then the inevitable happened. That's the Battle of Britain in 1940, where actually the Royal Air Force were outnumbered. They had about 600 planes, and the Germans were coming about with 2,000 planes, the Luftwaffe, the German Luftwaffe. And the thing is that, as mentioned before, so you had 100 miles of range, and you had 30 minutes of warning. Where the Germans were wrong is that the system, just to go back for one more slide for a second. So if you go back one more slide, the system, as you would look, the Germans consider that these systems or these radar stations were not working together, but that was not true. And the system was that all these 20 stations were actually gathering the information and sent to the control room in Uxbridge. And as usual, there were mathematicians sitting there doing some probability. That means that although their system was not quite accurate as nowadays, they were able to, based on all the 20 stations, information was coming in from 20 stations, and based on that, they were able to track the German bombers. And then what they were able to do is send always intercepting the bombers with fighters, and they actually won the war with this kind of system. So this was actually the biggest thing in the German, well, that's what the German underestimated the British, that they had these radar systems. And this is when actually the quote of Churchill, it's very important, is based on this radar system and on these airplanes, that never in the field of human conflicts was so much being owned so many to so few. So actually there were few fighters who were able to counterattack the German bombers. And this actually one of the key turning points where actually the Allies won the Second World War. This was one of the ages. Okay.
Question.
Yes.
One question is
Yeah.
that so the Germans could not believe that this thing could work.
No, they thought actually the Germans had such a similar system,
Okay.
but was never connected. That means that this was actually, you can say it's an ancestor of sensor fusion.
Yeah.
So if you have, what they did is the following. So they had actually there, I will show you in the last slide, this radar system was not perfect.
Okay.
It's the probability of misdetections and other things were a big counterpart of these radar systems. But what was good is that they had 20 of them. So they were not very directive, but they were able to see, okay, something is coming from that direction. And they had 20 of them, and all this information came back to this Uxbridge control room, where they tried to set up a priori estimation where the bombers are coming from. And then they were able to radio the airbase, and they sent up
That was the secret.
Yeah, well, it's not a secret, but the Germans didn't think of putting all this information together and to work as a system. So the Germans used all these radar technology one by one for a single station, and everything was connected. That was the biggest point. And also from the control room, they were able to radio all the airports where to start which fighter, and then how to counteract or how to intercept the bombers. So they weren't believing that the UK had such a complex system with all the information and all the communication parts set up with that. Okay, but let's go on. So what was the problem with these radars? So it was working, and they were able to shoot down not all of them, but most of them. The problem is that, as you see, we'll talk about that a little bit later. That's going to be a little bit of physics. The frequency, it was a low frequency. That means it had about a 13 meter of wavelength. That gave you a very low resolution. That means that if you have, I'll give you an example, if 3 bombers are flying together, that this system is not able to distinguish between them. That's one of the biggest points. It had ground clutters. That means that you had some misalignments or missing targets or wrong targets coming from bounces from the ground as well, or from clouds. That's the biggest problem. It had a very bad directional finding, so it was able to maybe look into a degree of 20 degrees or something like that, but not that direct as a pinpoint out where the bomber is flying at the moment. Also, if you would think about it, how do I want to continue with this? I'll go back just a little bit again. So if you want, this is a size where this is actually a pole for electricity. You can see the size ranges. And if you want to put this on an airplane and you want to use it on the airplane, that's not possible. So basically, that was one of the biggest problems, that this was too large. The system that they developed, they cannot really, how to extend the system to mobile solutions. And at that time, that was one of my questions from the audience. So they used klystron tubes. That was the biggest idea. And that's how they generated the most of the things. and I mean the frequency, and then came the solution. They had to reduce the wavelength from 30 meters to 10 centimeters. And this funny thing, which is about this big, this is called the magnetron. This is actually, you have the cavities here, and you can generate technically a much faster, larger frequency. That means smaller wavelength. And this was able to, you can put this already on an airplane. Because I will talk about this in general terms. If you go for lower frequencies to higher frequencies, the size of the antenna is actually reciprocal proportional. That means if you have higher frequency, you have smaller antennas. That's the story behind. And just as how the UK helped the US, it's an interesting story, how they helped win the World War is in 1940, there was a Tizard mission. Henry Tizard was one of the lead scientists in England, and he went to the US, especially to the MIT. This is when actually MIT started. And to get actually a lot of knowledge, they brought 4 things back to the UK, from the UK to the US. One of them was the magnetron for the radar system. The jet engine was very important for the fighters. They had the theoretical background of the atomic bomb. And the third one is actually, that's one more intense story. It came all in the black box. That's why you say in the black box, you have in the airplanes, you have black boxes. This comes back to this 1940 story where the British brought their secrets to the US. And then the US won the World War with the help of the US. This is actually the story where Tizard is explaining to some of the US physicists the idea of the Plystron. Okay, so that was the idea. And this was let's say, the birth of the radar systems. And I brought 3 nice stories from the past about the radar system. The one of them is relation to Hungary. So where did Hungary contribute to this radar system or the radar development? It was in 1945. This was the first moon radar experiment. It was done by Zsolt in Hungary. Then he went to England and to the US. So this is where what he did is that he set up an antenna, a very big one, and he said that he should be able to detect radio waves bouncing back from the moon. And the proof of concept, after the theoretical calculations, he was able to receive the data and it wasn't the data, but technically only a small impulse, and then the received radar waves were actually also measured. And based on these results, that was the birth of radio astronomy. So this is how technically nowadays people do that. So actually, it is possible to detect objects from far away just by getting the reflections of the microwave.
Where
Yes.
was this done?
Where?
Where?
Good question. It was in Budapest, I think, and it's one of the laboratories of Zsolt. I don't remember which one.
45.
In 1940, yeah. And
It's not
45,
building. So there is a big US university building E, which have not this an advanced version of this thing.
I think I think they reproduced it. Yes, there was a story that they reproduced this later on. Yes, but they didn't do it from there.
Actually, that has helix on it, not this.
Yeah.
Was.
Yeah. That's the story. Yeah.
So they also probably they reproduced the experiment on building E, but that was not from that.
Yeah, but 1945, that was a
Yes.
big thing, and now it's less of a big thing. Yes. Okay.
After the war was ended, so 1945.
Yes.
Then after.
Yes. Okay, so this was the moon radar experiment, and that's what the Hungarian relations between radar. The second story, which I really like, is when you talk about Chernobyl. You usually think about the atom reactors meltdown, but in Chernobyl there is also a huge radar. As everything the Russians do, it's huge. And if you look at the size of this, is just get an idea. The length is about 700 meters. That's about 2,300 feet. And the height is about 150 meters. That's 490 feet. So the size of this radar, what they had in Chernobyl. And it used about 10 megawatts of power. It was short radio. And they were able to detect missiles. And it was working until 1989. It was actually had a range about 1,600 miles. So it was a very long range radar. This was used for a certain time. Then it actually went. They set it down after Chernobyl, and actually you can also visit there. It's just a relic from the time. But the Russians were able to produce such. But you can see the size again. If you want to put this on an airplane, it's impossible. but it's very important that I will explain why. But for long-range radars, you need to have low frequency, because those frequencies, lower frequencies, travel better through the air than larger frequencies compared. I will talk about this, why this is important later on. Okay, but this was a good story about this. And the third story, which I really, really like, this is one of my favorite ones, is there was a famous F-140, 117A shoot down in Serbia. It was in 1999. The story is the following, that you had this Lockheed F-117 Nighthawk plane. As you can see, it has a very funny shape. It's very simple. When it flies, you have to have all the planes, it's aligned that way that it reflects away the waves and not towards the radar. And also the material, what is it made of, is actually absorbing the micro electromagnetic waves. And you're not able to, it reflects something, but with a very small amount of energy. And this was the only case when such a Nighthawk was shot down. It was in 1999. And the thing is that usually when you want to find such an airplane with a radar, that's like finding a needle in the haystack. That's impossible to do. And it depends. If you ask the Serbian war, if you ask them how they shot it down, they always explain some very complicated stories and how they were able to have some specific radar technology. No, that's not the story. At that time, the NATO was so optimistic about this Nighthawk that's undetectable. They didn't take any security measures, and they made 3 big mistakes. The one of them is that the Serbians, actually, this is the lieutenant colonel who shot it down. I think it was also Hungarian or partially Hungarian. His name is Zsolt. They knew that the airstrike was coming with about 3 or 4 Lockheeds. They knew how the plane was generally flying, so they had a lot of preliminary informations, and they had luck, because they were using low frequency radars. And when this Nighthawk opened his bomb bay door, that's when they become vulnerable. And that's what they were trying 3 or 4 times to find the Nighthawk. They knew that it should be there, but when they were putting down the bombs, that's when they found it, and then they shot it down. So actually, this is actually, you have to, once again. So basically, the Serbs had too much information about the fight plan, everything, so they just had to find it where it is. Yeah, sorry.
Was it just an SA-75, like basically the second generation of the fairly old Russian air defense systems?
That was one more thing. Yeah, that's
yeah. They had a low frequency, and also they had people on the ground in Aviano, and they gave a phone call when the planes took off.
Exactly. So a lot of things played together, but the biggest problem was that NATO was making a lot of mistakes. Yeah.
What I've heard is that they actually modified this as low frequency, so they actually tuned it to the general size of the entire airplane. And
that's one. Yeah.
But it's created some reflection.
Yes, but you have to know that it's there, and you have to look at it.
Yeah. Could not scan it. Was just to find it, and then
yes,
for the fire projection, whatever, to actually lead that.
Exactly.
That was the trick, which I think that was the secret, that they actually knew the physical size of this thing, and they could very.
Yeah, pretty much that's it. Yeah, and then of course, if you go to the Belgrade Aviation Museum, you can. It's the only time whenever Lockheed was shut down, but this was mostly as usual. It was partially a human mistake. So that's or a chain of human mistakes, what you should not do in general. Okay, so this was my part of the history of radar, and now let's see how radar is really working. So what's the goal of radar? So I'm going to try to explain it in very simple terms, and then as we go deeper and deeper, things will get a little bit more complicated. But I hope there will be questions and I can answer them. So let's start with the very basics. What do I want to do? Let's say I have a radar system. What are the main objectives I would like to do? One of them, there are 4 things I would like to usually use it for. One of them is I want to detect, that's the most important, the range, how far an object is. I want to detect the size, because that's also important. Is it a bird or is it a bomber? I want to know the speed. and I want to know the direction, where is it coming from. These are the 4 parameters I want to estimate from some kind of a measurement. I didn't tell you too much about it yet. And the source that I'm using, I think these terms are pretty much everybody who watched any type of military movie is familiar. You have the radar, you have the LiDAR. The LiDAR is more currently into automotive industry, and you have the sonar. These are all, but technically, if you look at it, it's always some kind of a wave detection and ranging. You see navigation and ranging, detection and ranging. So it's always detect something and to estimate the range of these things. The difference mainly between radar, LiDAR, and sonar is the wave it's used. So basically in radar, you use electromagnetic waves. In LiDAR, you use light, which is also a special electromagnetic wave, but with very high frequency. And you have sonar, which is sound. And also in water, sound travels better than electromagnetic waves. That's the only story behind it. Okay, but let's focus on radar. That's what we're looking at. The other things are just, these are pretty much the concepts are very similar. You want to do the same thing. The source of the signal you're using to measure, that's different. So let's focus on radar, and we want to measure the range, the size, the speed, and the direction. So let's start with range. How do I detect? But first of all, yeah, sorry, this is what I wanted to mention. So let's start with a little bit of physics. I won't go too deep, but it's important to understand what is the relationship between frequency and wavelength. So if I look at this simple chart, the thing is that if what you're using is technically waves, that means you have sinusoid electromagnetic waves, which is some kind of an oscillation. And if you look at this, the frequency, if you go up, it's actually, if you can put it into simple terms, is that if you have 1 second, how many times the wave actually oscillates throughout time. If you have a smaller frequency, you see you have less sinusoid components. If you go upwards, you will have 12 oscillations. And of course, the wavelength is technically the length of one period of this sine wave. That gives you, if you have a high frequency, you see the wavelength is short, and the opposite, if you have a low frequency, the wavelength is long. That's what I actually mentioned, that in the beginning of the radar systems, they use radio frequencies with low frequency. That means this has a longer wavelength. That's going to be the story. And in order to see where we are, so basically, if you go from 300 kilohertz up to currently the automotive industry uses 77 gigahertz, you see that about here, you have a wavelength about a little bit smaller than 10 centimeters. That's where you will be. And if you go on, you have the microwave and your ultrawave and so on and so on. You have the visible region over there. That's where the light is. So, but currently in radar systems, we go up to that 300 gigahertz. That's a bit too much, but we are not able to produce those. But we go up to 150 gigahertz. That's the highest frequency that we're able to use. But that's what's very important. So basically what you have to understand is that the higher the frequency, the faster the changes between the up and downs are. That's the story. And that's what we're going to look at later on, because this will play an important role to see that how these electromagnetic waves penetrate through the air or through clouds or through materials. That's going to be very important. So let's see, how do we do that we're able to measure the range, how far the object is. This is a very simple concept. Instead of measuring distance, we are measuring time. What do? As actually we can do the same way. We clap, we create an impulse. This is actually the impulse is generating the radar system, and then it listens. What's coming back? Technically, the bats are doing the same things, but it's ultrasonic. So you have a short impulse, and you're waiting for some reflections. You will see, and then you're transmitting again a short impulse, and you're waiting again. And basically what you have to measure is you have here 3 targets, and you have to measure the time it takes in order to travel this amount of time. And it's very important. You know that the wave is actually going with the speed of light. You can measure the time. It's very simple math. So from the time, and you have the the speed, you have to know that, okay, it travels to the object and it comes back. That's what you have to do. It's technically the light of speed times time divided by 2, and you have the distance. That's a very simple math behind it. So basically, the biggest idea is that you're technically measuring. That's what the English were doing. So they were actually trying to find a simple peak in the return signal and then measure that. The only thing is that, of course, if you were transmitting, you have some range resolution. That means that as you go further, that's going to be a little bit of a problem. That the signal is actually, if you go further, it will have a higher attenuation. So targets closer to the radar is easier to detect than further ones. That's going to be very important. But okay, so that's the general rule. If you want to make generally calculate the range, how far my target is, all you have to do is you simply clap, you listen to the echo, and then you measure the time, and from the time you have the distance. That's the basic rule. Okay, the second one is anyone can make a wild guess. How would you measure the size? Somebody can say, okay, from the size of the amplitude of the response. So how big is my echo? But that's going to be problematic. Why? And that's going to be important. This is where another term will come into the play. Is basically the reflection of any electromagnetic wave. It depends on many things, on the material, the physical size, the shape, the antenna, and so on and so on. So basically, this is what I give you a heads up. If I look at these, and I'm going to explain this in a short term. So basically, you have different type of airplanes, and what you see here is that if you take a radar picture of this airplane and you take an equivalent sphere, how much is the reflection? That means that this is actually, if you look at this, the size, these are sizes are pretty much the 1-to-1. And if you have here, this is what the lockhead is, you're trying to find a sphere with about a surface of 0.025 square meter. And if you look it up, if you have the B-55 bomber, that's a 100 square meter. That's pretty easy to find as you look at it. But it doesn't depend on the size. It depends on the material. It depends on the shape, and so on and so on. So basically, this is what the radar cross-section means, that if you have any type of object, can you set an equivalent sphere, and how big is the diameter of this sphere? Okay, so basically this is what you see here. So if we take such a large airplane, a B-52, you will have about this big of a reflection. And if you take this lockhead, the smallest one, you have technically this about like a bird as a size. Although the size you can see, this is actually, you have here the MiG-21, that's actually smaller, but it has a larger reflection. And it's actually 4, this is 0.025, so that's about 1%, something even smaller about that, below that. Okay, so basically, and you can see there's one more picture. I usually, those of you who are familiar with antenna characteristics, it's also important if you have an airplane from which direction you are getting the radar picture. As you see here on the side, you will see that from the front, it's easier to detect than from from a certain angle. Also from the sides, it gives you a larger amount of power. It depends on which angle you're hitting the airplane at the moment. Okay, so these things play an enormous role in the received electromagnetic wave. It's not simple. It's not just simple. Just okay, let's take an airplane, and now okay, you can tell me how much is the received power, and I can tell you the shape. So you also have to consider which direction you're hitting the airplane, also the material of the airplane, and so on and so on. So the size is not directly detectable from the received signal. Okay, so I think we covered just quickly the range and the size, and let's look at the speed. How can I detect the speed? That's an interesting story. That's simpler because actually the English were only using it for range. They didn't care about the speed because you cannot detect directly the speed from that received power. That's how the police are using. That's what the police don't care about the range. They care about the speed. They want to charge you not for how far you are, how fast you're going. And the idea is following the same thing as if you're hearing any type of policeman or an emergency car. When it's coming towards you, you always hear a higher frequency. When it's going further, you see a lower frequency. That's called Doppler shift. That means that if you have a sinusoid wave, which is constant, not an impulse like, you have a constant wave, and if the car is approaching, then technically the wave front is pushed back. So that means that you have a higher frequency. If it's going further, then you have a lower frequency because it's actually the reflections are smaller. And you're trying to detect this frequency change in the signal. That's going to be, and that's how an the CV, that's a continuous wave radar works for policemen. They are just measuring the frequency difference of the received and the transmitted signal. And if it's higher, then it's going towards you. If it's lower, then it's moving away from the radar. That's the idea. Okay, but I was talking about currently, I talked about pulse radar and I talked about continuous wave radar. One of them is able to detect the range. One of them is able to detect the speed. But I cannot really relate to how do I get both if I want to have both? Because now in modern automotive industry, so where you want to have autonomous driving, you need both. You need to how far the car is behind us or in front of me and how fast is it going. That's going to be a little bit more tricky. So again, just to visualize the things. So here are the pulses. This is what is used for pulses, and then you have the received signal, that's the range, and you have the continuous waveform, that's able to detect the velocity. And now if you want to combine both advantages, you want to have range and speed, you want to have an FMCW radar that's continuous, a frequency modulated continuous waveform. That means that the signal's frequency is changing in time. As you can see, it starts with a slower frequency and it starts to speed up. That's what it's using. And with if you look at the time and the frequency of the signal, the red one is technically the signal that's sent out. The green one is the one that what is bouncing back from the object. And in this sense, if you look at this plane, you have two shifts. One of them is the time shift because you can actually tell which signal point is correlated with the other signal point. So from that time shift, you again have the range and the frequency shift, which is where the signal is moved up or down. That's going to give you the velocity. Of course, the thing is that you will ask that why didn't they use FMCW radars in the Second World War? Always that to detect such things in frequency and time domain, you need an FFT. So you need some kind of transformation and you need digital signal processing. So at that time in 1939, everything was analog. So now, as you have an FMCW radar, that's what is using in your car. If you have a modern car with autonomous driving, you're using FMCW radar because you need a vast amount of signal processing. You have a lot of data and you need a lot of signal processing. So this is what the next step of the radar is FMCW radars because they're able to detect speed and the range together. That's the biggest thing about it. Yes.
Some of the rumors, which at least I've heard, was that nowadays they try to use radar to identify the kind of airplane. Apparently, maybe I would like to just kind of get whether that makes sense or not. The different airplanes, the surfaces vibrating on them as they fly, they have different characteristics of vibrating surfaces. And literally by looking at the Doppler distribution of those
that's micro Doppler. Yes, that's one more thing.
Yeah.
That's exactly so. If you want to detect how radars are detecting the difference between bikers and pedestrians, you have to look at the micro Doppler. But that's where you cannot do that analogously. You need digital signal processing, and you need even higher computation complexity. You can have the micro Dopplers, but that's going to be a big one more thing ahead. Yeah. Okay, but basically you have the conventional pulse radar, that's for ranging, and you have the CV radar, which is for speed, and you have the FMCW, which is actually more of a digital signal than an analogous one. Okay, and the last one is we have got range, speed, and we have size. And the last one is the direction of arrival. I think everybody knows when they were watching some kind of a like Pearl Harbor, any of them. You have the radar system, and you can see always this turning beam where the radar is currently looking. And the thing is that these are the classical radars. You have a mechanical rotator. That's how you do it, and that's how the analog systems were working. But the thing is that this is very cost inefficient, and you wouldn't put this on your car. This doesn't look good in general. And that's when currently we were only talking about the single antenna at the receiver and for the transmitter. If you have one antenna, the antenna is always directional. And that's when the story comes in that you put up a lot of antennas. This is called an antenna array, which is technically a lot of antennas, but the signal is phase shifted. That means that you send the same signal to each antenna, but with a different phase shift. That means technically you can move the wave without moving the antenna itself. So you have a lot of antennas, and you can actually move the direction of the wave without any problem. That's how your car is also sweeping the road, but you don't see that. You can these radars, you can easily see that it's moving around. In this case, if you change these phase values, if you have all the phases, then you're facing forwards. If you have a linear phase shift, then you're going to be facing towards another area. Also, this is only planar, but these are if you have antennas like this in a matrix, like 8x8 or 64x64, you can actually steer the beam in any direction, in azimuth or in the vertical plane. You can also see that if you have more antennas, your antenna pinpointing direction will be even better. So actually, this is actually, if I would move into one topic further, this is where 6G and 5G systems are also working, that your mobile phone is pinpointed out using such antennas where you are able to find and you can directly pinpoint you with the electromagnetic wave. That's the story. Okay, so basically this was the old systems with mechanical rotation, and now with digital beamforming, they was able to do that without turning the radar. So these radars are easily detectable. They are moving. These radars are not anymore detectable because they are not technically not moving. You see only the surface, and then behind the surface you have a large amount of antennas. Usually the example here is with 8 antennas. Usually you have 64 or even more antennas because you need to have a very specific. And of course, the size of this antenna will play a big role later on, but that's not that big. That's important. Okay, so and just a little bit about range, resolution, and operating frequency. As you see here the frequency going up from 0 till I think 220 gigahertz, and you can see that long range over the horizon radars are operating always at low frequency, just as the US or the British radars. And if you go up, you will find what's going to be interesting. Also, the GPR, the ground penetrating radars, if you want to find something in the ground, that also has to be low frequency because that's the wavelength that goes through the Earth. Otherwise, large frequencies don't go back, just go bounce back. But if you go up a little bit, you will see the automotive radars are at about 77 or 60 gigahertz. Why is that? That makes a little bit suspicious. Why do you have such a big frequency? That means that actually your range is going to be not that good. But what's important is that if you go up in the frequency, your wavelength becomes smaller, and that means your antenna becomes also smaller. So you have to do a compromise between range and antenna size. So if you have a car, you don't want to put a 30-meter long antenna on it. You need to have something small, and your car, the size of your car is given. So you have to have a smaller antenna for a car, and that goes about 377 gigahertz. And one more thing is that what you see is that the attenuation in the function of frequency. So if you go to higher frequencies, you will have larger attenuation through air. So you need more power in order to see to a certain distance. This will be a trade-off also. Of course, it's not linear, but you will see there are some bands where you can play with it. And there's one more important thing is that the range resolution. That's what I told you, that if you have 3 bombers flying together, the current British system is not able to detect it. And there's one more thing that I didn't talk about is that in the frequency, you always have a frequency band. How much of this frequency band you're able to use? If you have a larger band, then you're able to have a much smaller resolution. That means that the car systems, the current source system, have a resolution of 4 centimeters. That means that if you have 2 objects with a 4 centimeter difference, they're able to detect it as a separate object. Otherwise, it's going to be just one object. Okay? So that's the story a little bit here about the frequency and the application. Different frequencies, always you have to play a trade-off between size and range and so on in the given application. Okay, so a little bit, let's move on further from the four parameters, and let's move a little bit. This will be just short how the radar are placed, because first of all, as the British use the radar in a monostatic way. This is a very simple idea. You have one transmitter, you get the scatter from the airplane, and you have the same place you have the receiver. And the next idea was that why don't we use a bistatic radar? That means you have a transmitter somewhere and the receiver somewhere else, even closer to the target. This gives you a better range, and also for the weather radars, that's how they operate. You can put more receivers on different positions also. So you can actually split the transmitter and receiver for the radar system. And one more thing is that this is actually one of the newest, let's say the up-to-date technologies, the passive radar. Actually, you can use currently used TV or radio stations as radars. That's called passive radars. That means that here's my radar system, and this radar system, this is why it becomes from the military very important. This doesn't emit anything. So it just uses already given radio stations. Here's my radio station, here's my object, and it listens to the radio signal, and it tries to find the same reflected signal, and then from that reflected signal, it's actually able to detect the object. But this radar here, this is called the passive radar, it's not emitting anything. So you cannot detect these things. That's because currently a radar system you can detect because it's giving you a lot of energy out, and you can easily find that. Okay, so now we have the ideas of where to put receivers and transmitters. And just one more important or interesting usage is the SAR and the SLAR. Why do you put it on airplanes? You can also do that. You can actually use for some monitoring of the ground. That means that as the airplane goes through the surface, it actually measures the bounce. It only measures distance, and then from that you see this is actually I think it's a Navy ship. You get a picture of that, and you can actually see that from this difference of these A, B, C, D measurements, you can see that the ship has been detected 4 times. And technically, it looks like, from the airplane's point of view, that you have 4 transmitters, but you only have 1. But you're enlightening with this option and with this solution that you have more. Technically, it's a virtual lightning. This means that this part is lit 4 times, and from that you can actually get a pretty good object as a reference of that. And you can also see these are black and white images, but these are, I think this one is I don't remember which one. I think this was this is Los Angeles, I know. That one is, I think it's somewhere else. I'm not sure which country, but I think it was France. But you can get some pretty good images of the surrounding area of the ground. But that's the story. So you have a plane that's flying, and you have radar on the plane, and you can, from that, you can actually measure the terrain underneath. Okay, a little bit about the applications. So what do we have here? We have military, that's the primary applications. You have automotive. Currently, a lot of radars are used in automotive. Air and sea traffic is also one of them. You have also health. I didn't list it, but you can also do a lot of things. You can measure technically your breathing with the radar. It's actually also some kind of a Doppler shift. Also, you can do mapping. So like a SAR system, you can measure the speed, or the police is using it. So technically, radars are everywhere. You don't see them, but they are everywhere in almost every region of the scope. Okay, now we are actually able to do a lot of things. You have the cars and everything is working. Where to go further? So what are the options for the radar? What are even the future of radar systems? Okay, so that's going to be my last section. And the one of them is that currently radars I talked about as one singleton object. And what do you need to have a radar to do? And what are the options you have? So basically, in a radar, you always want to have a multifunction radar. So what do you want to do? So you want to detect. That's one thing. You want to track. Is that object still there? Is it still going? You want to classify. Is it an enemy? Is it something that's large? Is it a bird? Do I have to be afraid of? One more thing is that something new is also with cars. You have the radars. It's electromagnetic waves, so you can also communicate with radars. So we have car-to-car communication through the radar system. You can measure. You can also you want to have an image, and maybe what else is there? Is there interference? Is this a protected or some kind of another enemy? So basically, these things have to be incorporated into one system. So you can use radar for many things, but you want to have all these into one system. That's where currently the research is going. And one of them is that currently, if you have your radar system, how do you want to test it? Usually, you go out on the streets, like Google does, with the Google View, and you measure data. This is very expensive. And currently, where the research is going is that you're trying to have simulators or emulators. That means one of them is, you see here, this is actually a virtual reality, and you can see actually the car is moving there, and I think you will be seeing the trees. I hope you. Yeah, here are the trees you can see on the side, and this is actually what the car's radar is seeing from that virtual reality. So you place the cars. This is a more simple one. You can see this is actually pretty good with the 3D vision. This is actually from MATLAB. For networks, you have some simple blocks, and you can see that you're able to see the side roads, but you also have some false detections. These false detections, but these are all software simulated environments, but basically you can test your algorithm with it, and you don't have to go out on the street and drive hundreds and hundreds of kilometers. And the newest one, I just had a chance to in Karlsruhe in Germany. What you do is, as you look at it, the car radar is transmitted, and you see here you have planes which are technically absorbing the electromagnetic waves, and there are holes on the other side which are generating technically target-like responses. So you're emulating the targets themselves, and you're sending back a signal which if there would have been a target, then that's the signal what you would have gotten. So basically, these are all things that you help develop radar systems without going on the street with it. So you can actually emulate, and you can emulate movements, you can emulate other things, but you can actually also set up different objects, different sizes, and you can see how sensitive your radar technology is. But that's where the current research is going, because actually, if you want to get data, that's the most expensive in any AI solutions. Okay, one more thing. I think this would have been a question if I wouldn't address them. How do you use AI in radar? AI technically, the measurement in the electromagnetic don't use AI. That's the story. That's where you have the measurements, and from the measurements you might have seen. You might want to have some target classifications. This is probably a simple example that you have some pedestrians, you have bicycles, and you want to actually, from the microdopplers, you want to extract that is this a bicycle, is this a pedestrian, and basically you might want to have some kind of a machine learning algorithm behind it to distinguish between different targets. Also, one more thing is that you might want to, this is actually a SLAR image, and you might want to find objects like cars, buses, and so on. And this is where also AI plays an important role. Also, when dealing with electromagnetic waves, usually have interferences, maybe unintentional or intentional, and you might want to take those out. That's where also AI plays a big role. You don't want to do that the conventional way. You just want to have an AI system. And also with the tracking and the prediction, so wherever the target be at the next position, that could be also done by AI. But technically, the hardware part is given, so that's where you can also, maybe you can just with the AI you can extract some further information which are with conventional signal processing you weren't able to do. Okay, and one hot topic, Zoltan asked me to refer to this, is the quantum radar. So this was a hot topic, and this is still a hot topic because China claimed they have a working quantum radar. And they said in 2016, but nobody knows anything about it. There's no written, no documentation, nothing. They only presented it also in 2018. It looks like this, but as you see, it's never turned on. But the idea is puzzling. So how they want to do it is the quantum radar is based on quantum entanglement. That means, here's the example how it works. So the funny thing is this, it's on a quantum level. If you have two photons or two electrons, you can technically connect them. That's called quantum entanglement. And you can take apart these two particles. And if you put this away, this particle, and you do something with it, you will see the same effect on this one. This is actually for engineer, for everybody. If I tell you this, and the information that I change it here, it travels faster than the speed of light. That's pretty amazing. But where can I use it in radar? The radar systems, anything I told you until now, the analog part will stay the same. That's not you have to have an antenna, you have to have an electromagnetic wave. That's how it works. But how it works is the following, that you have two simple photons or for electrons, and you technically keep one of them. The two are entangled, you keep one of them, you send out the second one, but you have to, from the photon, you have to make an electromagnetic conversion. You send it out, and you're able to detect based on the reflection, you're changing back the electromagnetic wave back to photons, and you're trying to do some correlation between the kept particle and the received particle. And from that, this is actually, I'm talking about theory, okay? I haven't seen anybody done this. And based on that these two particles are connected. You can have many particles that are connected. You're able to do some correlation and find some similarities. And based on that, they say that if you have an airplane with stealth defense, you can actually track any type of aircraft with low power, because actually you're not looking at power, but you're looking on correlation of particles. But this is actually, you can only find papers, and there's one actual paper in Austria that they did it in laboratory. Okay, so this is where we are, and China said that they did it. But this is actually no one have ever seen. But if this doesn't say that your system of stealth is not working, it's just that you are able to do radar systems with lower power and higher accuracy. So your accuracy will be better, and also the power required for the system. But this part over here in green, that's the biggest task to do. So you do the photon or the quantum entanglement. You can connect the two elements, but afterwards, how do you do this part? That's the tricky part. That's what
Do you have to get back your photon?
Yeah. So basically, how it works, you entangle the two photons. You keep one of them somehow. That's already the big problem. And you have the second one. You convert that photon to an electromagnetic wave with a simple. There has to be a photon to electromagnetic wave converter, and you have the reflection. And here you have again a converter from the electromagnetic wave to the photon. And those photons which you receive, there are many photons, and you have also many photons that are entangled, and then you have to do the correlation.
So you have to get back a reflection to detect the decoherence?
Yes, you have to. That's how you, because that's when the change happens. Yeah.
Well, the other thing is that actually you don't have to receive it, but if you hit something with it, it basically made some change to that thing which you could detect.
Yes, but that's harder than to take the two signals and correlate it.
Yeah.
That's because then you have to measure the state.
To detect the decoherence, somehow you need to decode the second one.
Yes, it's cool. Yeah, that's what you have to do.
You just do the measurement, and when you do your measurement, you can see whether somebody has already did the measurement or not. That's the quantum entanglement.
Correct.
Yeah.
So if you basically can send this thing, and if it hits something, and somehow you can ensure that it eventually looks like it's doing the measurement, but of course I don't know if it's possible or not, then in theory you might, okay, not distance, but angle, you can see if it hits something. It's not necessarily has to reflect it.
So you did have
an idea, right?
According to the order, to the pair of that. Okay.
But there is no guarantee that this.
If this works, one more thing. If this works, there's one more thing that currently you can have also a smart target. You can also have an airplane. That's, I think military has done it. If it detects a radar signal, it can send back a radar signal.
But it cannot send back
This
something.
you cannot do. You cannot trick the system. Yeah, that's one more thing. Yeah. So that's the idea. So basically, if you ask the Chinese, I've looked through the internet because I was also curious. And there are some pictures, and there's only a statement that the Chinese did it, but nothing yet. They say it can look until 100 kilometers, but there's no real information. There's no papers, nothing. Okay, the Austrians in 2019 in Austria, there's one measurement which they have done, but it's in laboratory. So they have some simple measurements that's not yet practiced at the moment. Okay, but it doesn't say that that is not important anymore. Okay, so and just I bought a video. I will turn off this sound. 1 second. This is one of the companies. It's called Zsolt. And 1 second. And this is just what the future system will look like. Okay, so this is not yet here, but that's the idea, to go into this direction, that you have various type of radars and everything will be connected, and at the end there will be an AI which is making the decision. Of course, there's always a human at the end, so there is not the AI is going to, it's not Skynet, so that's important.
Yeah.
Okay, good. So thank you very much for the presentation. If you have any questions, I don't know if you will chat. Yes.
Question.
Yes.
The multistatic radars, especially FM and TV station-based multistatic radars. Some of the rumors we've been hearing is that, given that those are considered to be somewhat better to detect stealth aircraft because of the different wavelengths,
yes,
that some countries might be playing around with, such as what kind of background picture should I have for my announcer on the TV to have the kind of signal shapes to make it easier for the signal shapes to be used to detect source stealth aircraft?
Yes, that's
those kind of like messing around with it, like, yes, it's a TV station, but how can I a little bit mess with the signal shape to make it somewhat better for detecting?
well, where you can win with that if you make it as close as to a pulsed radar. That's just one thing, you have to turn it on and off. But actually, the current digital TV stations are perfectly good because they have very good correlation, and that's easy to find. So you have to have signals which are pretty good correlated, and doesn't have it is the analog part. So actually, you're using OFDM signals, and there you have the cyclic prefix, and that's correlated. So
and
the FM.
If I just happen to be transmitting my digital radio station with some GPS level time accuracy, then
that should be also enough. Yeah.
Yeah.
Yeah, that's the story. Yeah.
So where does BMS stands with it? So like where does radar research?
At BME, so it's not our department because I'm mainly, if you ask me, I'm mainly in the digital signal processing part. So if you look at me, I'm going to say I'm doing more on the after the analog to digital beamforming. So where we have some currently we have working passive radar. So we also try to simulate, but also replicate this passive idea. So is it able to use some digital signals from the COP hill? So we have the signal and then do it. And also with the military, as in Hungary, the military is getting more money currently because of the war. Currently, a lot of experiments are going in this direction as well, so into radar and other things. One more important thing is where we did research a couple of years ago is that if you think about radar, we were actually working with the border patrol, and we had a radar about this size, which had 8 times 8 elements, and that was able to detect people 2 kilometers ahead. So actually, it's pretty mobile. So actually, 2 soldiers were able to carry that around. But you have a range of 2 kilometers, not more than that. But these are actually collaborations. So the biggest challenge is usually if you're thinking about beamforming and multi-antenna radars, that's the analog front end. It's always the biggest tricky part to get the most power out of it, because the more power you have, better resolution. And you have to have more antennas, then you have a much thinner angular resolution. So you can find targets much easier and detect targets which are close to each other as separate targets. Yeah.
Somebody is noting from the remote viewers, one industry where you might see less rather than more radar is automotive, such as Tesla stopped using radars in their cars since 2021. They rely on cameras rather than radar.
Good question. I don't think they're going to stop. So actually, these things like LiDAR, the cars are using LiDAR, I think, at the moment. You can have cameras and you can have radars, and these things, let's say, they are not concurrent to each other. They should be used as in conjunction with each other.
So you should show some real radar images.
Yes.
And compare to the visual counterpart.
Yes.
And it's much harder to detect anything on the radar.
Yeah, that's true. That's true.
So
but
this is what Tesla said, that it's giving so much noise that basically, at least in my car, is turned off.
Well,
they are fully on video.
Save money, but they are still at level 2.5, and Mercedes is at level 3, and they have radars.
Whatever, but if you just look at that,
yeah,
but my car drives me home. I know Mercedes is at level 3 and my car drives me home, but that's a difference. That's a different.
Yeah, these are
questions. Look at that, right? That's
also the problem will be if everybody is using radar. So if you have a lot of cars using radar, they interfere with each other. So there are things which have to be played out. This car-to-car communication, that's going to be the biggest. How is going to be your Tesla? How is it going to communicate with your Mercedes?
So basically, all the phantom brakes and everything, it's attributed to those things.
Yeah, those
under bridges and whatever, they got messed up and they said, okay, cut it off.
Tesla. Yeah, I know the story. The Tesla had a problem with it stopped somewhere in the middle of the road for no reason, and actually it was because the radar electromagnetic waves. If you have these you have these metal things on the road. What is it called? What's the English term for that? For the sewers. You have the metal that reflects also. So these are tricky things that you have to play with. That it has to be high enough, and also if your radar is pointing down, then you have a reflection from these sewer tops. These are questions that But if you have a bad seeing condition, for example, it's better than nothing. I wouldn't rely on any of them. That's true, because if you have rain, then your LiDAR is bad. If you have the radar is not really these automotive radars are not for long range, so you won't see hundreds of kilometers in front of you. But I do think that to take all of them and to do some sensor fusion and to make the decision based on that, it's not a bad idea.
Rain because of scattered light.
Yeah. Also with the rain, there is also a problem that it depends on the rain. So if the raindrops are comparable to the size of your microwave wavelength, that's always a tricky question. So basically, if you have a short wave, if you have small frequencies with the British with long wavelengths, they don't care. It doesn't matter. The range doesn't matter. But if you have short wavelength with high frequency, that's an automated radar. Then you have a rain. That's a problem. That's rain. We also had this experience when we were playing with this border patrol radar. We had a problem that we did our measurements first. We brought it out to a field, and on the day before it was raining, so the grass was wet, and that means technically we saw nothing. Yeah. So these
I remember. So I rented some I don't know what, and we drive in a massive rainstorm, and it continuously said forward collision.
Exactly.
Forward collision. So I had to turn off the whole thing.
Yeah.
Because it just, and this thing is in production, and this thing is in
Yeah, probably if you're driving in Malaysia where you have monsoon, that's probably not going to work. But
it was in Idaho, but
okay, yeah, but same problem. Yeah.
Illinois, whatever.
Yeah, but the question is what works. That's all. Question is what helps in that case?
Yeah. Nothing. So this is the same with Tesla and the vision stuff. So it is actually stops working when you either don't see anything because of the sunlight. So this is you drive and you literally see nothing. Then unfortunately the car won't either.
Yeah, that's the
That
problem.
simple.
Yeah.
So there's no magic.
It just helps you. That's why it's
For those radars which need all the digital signal processing, I mean, are people just using ASICs or with FPGAs? What kind of components do they use for this?
It depends. I always want to use the cheapest one.
Sure.
To be program, but depends if you need to have a fast processing in FMCV radars. If you have the multi-antenna arrays, the amount of data is basically that's where the microcontroller stops. So you need an FPGA or some kind of an ASIC, yes, because the amount of data that's coming in from the different antennas, you have to have the range and you have to have the speed and other things. So you need to have a lot of data, which is calculated pretty much on the big data sets. You need to have fast calculators. You need the FPGAs. Yes, pretty much.
And the kind of calculations we need just linear algebra. What do we need to get?
Good question. Mostly general algebra. Yes. Of course, there are some things like clustering. If you're doing a radar sweep, you always have detection points, and you need to also see which points are belonging to the same target.
That's also kind of linear algebra.
Well, technically, yes. Yes. So nothing else. The FFTs, pretty much. Just basic stuff. Yeah. Yeah, on the point. But it's a lot of calculations, although it's linear algebra. Yeah. Yes.
Yes, I have a question. So you're here for how long as a Fulbright scholar?
Yes, for 5 months.
5 months.
Yeah, I'm a second generation Fulbright scholar. I was here with my father. Some of you have met him. His name is Zsolt. I was here in 1993 and 1994. I was 12 years old.
Your father was in California? No.
Yes, he was. Yes, he was.
Stanford.
He was at Stanford. Yeah, he was working with Professor Widro. Yes.
And so what are you an academic? What is your home institution?
The same as my father's, Technical University of Budapest. Yes.
Oh, okay.
I'm the same.
Okay.
Yes, I'm in Budapest, the Technical University. Yeah.
So you're teaching and you're researching.
Yes, exactly.
And then I had another semi-technical question, because you haven't. Some of the military applications that we have, I think we're supplying. Just started reading about it. A golden shield, or I think to Israel, or reading about it, or possibly Ukraine as well. Is that based on this technology?
Good question. I'm not sure. I have to check on that, but probably if it's a radar, I would be when people ask me as an academic to develop radar systems, I have no problem with radar systems. But as soon as you need to have fire control, I don't want to do that. Yeah, that's where I draw the line. I don't want to shoot. The detection, I'm familiar with that, but yeah. But there was one story. My father in 1986. The military came to him and he asked that, is it possible to detect people behind walls using electromagnetic waves? And my father thought about it for about a week and he said no, because he knew what they were using for. It is possible because you can detect actually breathing people, or heat. But my father didn't want to participate in it, so he said, nope, not possible. But usually it's a question of the usage, Because here the radars are.
was.
If you have metals and not, yeah, but they didn't have to go that deep with the scientific explanation. Yeah, because actually here in the radar systems, with the drones and with all the rockets, everything is technically radar based. So over there, how they're flying, how they find the target, that's also all radar based. But that's what I say I don't want to participate on that part. Yeah. Okay. Thank you very much, then. Thank you.
Please have some drinks. Well, it should have